So carbon-14 dating is a way that we can estimate the age of fossils and other artifacts. This is exactly what is done in order to determine the age of various fossils. So carbon-14 is something that is present. It's a radioactive element that's present in living organisms at a certain rate. And it has a half-life of about 5,800 years. I think I looked it up. It's like 5,730. Just for ease, I rounded it up to 5,800. And that's long enough to be like well within a span of a significant number of fossils. And because life forms are carbon-based on Earth, there's a lot of carbon that's had. So this type of dating works for a large number of fossils. Once you're too far in the past, though, there's maybe not enough carbon-14 to detect well enough, or you can use other techniques like where they're located in the strata of the Earth's crust. Anyway, it can be shown that carbon-14 decays according to this equation. A of t is A naught e to the negative 0.00012 t, where t is in years. A certain fossil has only 10% of the expected amount of carbon-14. How old is the fossil? So when this creature died, it had 100% of the expected amount of carbon-14, whatever that amount was. Like an elephant would have more carbon-14 in it than, say, a mouse, right? So it had 100% of its expected carbon-14 when it died, and as it laid, it decayed. And now we dug it up and we did a test, and there's only 10% of the carbon-14 that we would have expected to find. So we can use that to determine how old the fossil is. So let's look at doing that. Now, like when we do half-life problems, it doesn't actually matter how much it started with. All that matters is only 10% is left. So if the starting amount was 100 grams, then only 10 grams remains now. So that means my A of t equals A naught e to the negative 0.00012 t. 10 grams remains now, 100 grams started. If I divide by 100, that gets me 0.1 on the left. So again, it doesn't matter how much you start with, because once you divide, you're always going to be left with 0.1 on this side because only 10% remains. All right, take a natural log of each side. Why do we do that? We do that because logarithms let us pull powers down as factors. So I pull that to the front. Why do we want to use log base e? Because here I get to say, oh, that's 1. So I just have the natural log of 0.1 is negative 0.00012 t, which means t is natural log of 0.1 over negative 0.0012. So if I plug this in, natural log of 0.1 divided by 0.00012. So I divided by positive instead of a negative. So this is approximately 19,188 years old. So even with 10% left, I'm already back to 20,000 years, right? So that got me pretty far in the past. Do a quick think about this. If I wanted, so I have 10% left, right? If I had half of it left, then I'd be at 5,800 years. And then another half of that, so that would be a quarter left. Another half of a quarter is an eighth, right? So that's 3. And another half of 1/8 is a 16th. So this is, I would need a little bit more than a 16th, but less than 1/8 left. So somewhere between 3 and 4 half-lives, which this is, right? This is 19,000. So 19,000 divided by 5,800 is 3.3 half, 3.3. So I basically did 3.3 half-lives because I divided in half a little over 3 times. Okay, so that's another way to think about the half-life decay. All right, so almost 20,000 years old. And this is the exact type of thing that they do on carbon dating. Now, they don't sit here and solve this equation every time, because here's your percent left, here's your parameter K, so you can always find how old it is easily. For actual, like, dating things, they're not going to use 5,800. They're going to use 5,733 or whatever the actual number is. And they'd have a lot more digits on this parameter here, so they get a finer answer. But for our purposes, this is good. It's about 20,000 years old.